Okay, we will get to three-space vectors later, but we're going to start with vectors in a plane. Okay? Those first two, law of sines and law of cosines, will be on the quiz along with this section. Now, we're going to cover a lot of terminology today, so it'll go a little bit quick. We'll finish up the last of some of the harder problems tomorrow, a couple of those, and then you're going to have the rest of tomorrow to work on this stuff. Okay? So, when we talk about vectors in a plane, anybody know what a vector is, first off?
Is Tracy Lansing here today?
Anybody know what makes up a vector?
Direction and magnitude.
Direction and magnitude. So magnitude is represented by the length of the line. Direction is just literally which way the arrow is going. Okay? So the way we're going to generate these are just a directed line segment. So it's a line segment that has an arrowhead at one end. Okay? So you have an initial point, a terminal point. The arrow is obviously pointed towards the terminal. Now, because these things only have those two properties, they don't actually have a property of position. You can put them anywhere you want. So if I'm representing these on a plane, it doesn't matter where they start, as long as it's the same length and it's going the same way. So what that translates to is you have the same length as well as they're parallel. So all five of those vectors are actually considered the same vector. They're equivalent to each other. Okay, they're just translated. They're just slid around the graph a little bit, but it doesn't change what they are. Okay. They will also represent this with the kind of arrow over that PQ. They'll also do that length or magnitude. They'll put double absolute value bars around that. Okay, that's just the notation they use for it. Now, they'll also rewrite these so you're only dealing with one letter instead. Okay? So, if I have all direct line segments that are the same as this PQ, rather than say from that specific point P, because that point P could be at 7,8 and Q be at 25,4, and you have a line going from one to the other. But since you can reposition it, they'll label it as V like this. Now, the book will do this as a bold V. It becomes a massive hassle to try to write a bold letter on all your homework and all the tests. So when you're handwriting it, they'll put an arrow over that as well. So if you have a single lowercase letter with that kind of half arrow over it, that means it's that vector that no matter where you put it is equivalent to PQ. Okay? And they'll typically use UVW for that kind of stuff. So, if I have two different vectors, U is the vectors from P to Q, V is the vector from R to S. If they're equivalent, then they should have the same what? This or length, distance, yep, and slope, direction. I can represent the direction with the slope. I can represent the magnitude with the distance formula. So, what's the slope of P to Q? Well, how do you find slope?
I can't remember.
Then you're going to be hurting a bit. Yeah, subtract the x's, or subtract the y's on top, then subtract the x's on the bottom. Make sure you keep the order the same. So to keep it consistent, I would just always do terminal minus initial. So in this case, the top you have 3 minus 1. I'm sorry, 1 minus 0. What am I doing? 1 minus 0. On the bottom you have what? 3 minus 0. So you get a slope of 1/3. Then if I'm doing the slope for the vector v, what do I have on top?
3 minus 2.
3 minus 2 on the bottom. 5 minus 2. So you also get 1/3. They have the same slope. For magnitude, what do I do? Anybody remember the distance formula?
Square root of x, 1 plus x, 2, and then square it. No, there's a minus sign.
Minus. Again, it's the differences for x's and differences of the y's. Square them both, add them up, square root. It's actually the Pythagorean theorem. Okay? It's a modified version of it. So if I want to do the magnitude of u, I'm going to do the square root, so basically that number squared, is equal to the differences, so 3 minus 0 squared plus 1 minus 0 squared, and square root it. So you're going to end up with the square root of what? 10. 3 squared plus 1 squared is 9 plus 1 is 10. So when I do the magnitude of v, I should get the same thing, because I'm going to, again, just basically take these two values I had here. So I'm still going to use those top and bottom slope values. So I'm going to do the 5 minus the 2 squared and 3 minus 2 squared. And again, I get square root of 10. That's enough. I'm showing their directions the same, and I'm showing their magnitudes are the same. Does that make sense? Okay. Now, it becomes a real hassle to always have to write the vector from P to Q and define an initial point and a terminal point. So because we can rearrange these anywhere you possibly want, a convenient place to move them is so that your initial point is on the origin. Okay? By moving this to what's called standard position. So the initial point's at the origin. We get what we call the component vector, or component form of the vector. Okay? What this means is that if I have it starting at 0, 0 and going to some point, doesn't matter where, since I am going to imply that it starts at 0, 0, I'm going to show that with these arrowed brackets. If I have these arrowed brackets, kind of looks like a less than greater than sign, but if I have those around it, that just implies start at 0, 0. Stop at whatever this is. So if they ask for component form, that's what they're talking about. This also just makes it a lot more convenient to work with. So you're not having to deal with the initial value. You can rewrite any vector as being this component form and then deal with it from there. So you'll have that vector v is equal to whatever those two are. Okay? Because of that, your line P to Q, rather than writing all this out, you can actually just write out that rearranged one at 0. All you have to do is take the terminal minus the initial for both the x's and the y's. That'll automatically reposition it. Okay? Magnitude-wise, instead of bothering with that, you can actually just square both pieces. Square the x-coordinate of that component form, square the y-coordinate, add them up, square root. Now you can do this form if you like, but if it's in component form, this is easier than dealing with the zeros that you don't care about. It's subtracting 0 anyway, right? Now, you also have what are called unit vectors. A unit vector just literally has a length of 1. Unit vector just has a magnitude of 1. It's not talking about direction, it's just talking about having that magnitude of 1. And a 0 vector then would have a magnitude of 0. It does become minorly useful in some cases. We'll get to those later. More so in 3-dimensional than in 2. Okay? But it still just represents a point somewhere in space. Or more specifically, a point at the origin, because any point's equivalent. So lastly for this part, if I have two vectors then that are the same, that means the only time they will be the same is if when you put them in component form. So when you move them to the origin, they have the same x-coordinate and the same y-coordinate. Which makes sense. They're literally over top of each other if you graph them starting at the origin. So if I have something like this and I want component form of and the magnitude of this vector. Okay, well, all I'm going to do for it is take terminal minus initial. So, what am I going to subtract? Yeah, negative 7 minus negative 2 and 9 minus 3. That's going to give me the vector what? Negative 5, 6. There we go. Negative 5, 6. Then if I want the magnitude of that vector, I'm just going to square both those and add them up and square root them. So I end up with the square root of what plus what?
25 plus 36.
There you go. Which gives you a square root of 61. Okay. And can I simplify square root of 61? No. So there's your component form. There's your magnitude. Okay. The arithmetic today is not too bad. It's just keeping track of all the terminology. Now you also have vector operations. Now I honestly think of vectors a lot like matrices. Okay. It's a combination of things that are all put together to represent one concept. Matrix is a combination of numbers that represent that overall whole. Okay. So some of your same properties apply. Scalar multiplication, just like with matrices, scalar multiplication of vector just means you have some number out front that you multiply times everything inside the vector. So that makes it very simple. All you do is multiply everything times k. Vector addition works the same as matrix addition. You just add all the corresponding components. With a matrix, you have a lot more of them, but with this, you just add the x's, add the y's. Now, when you have that multiplier of k, though, one little bit oddball thing that happens, if I multiply times k, that's only really going to affect, it'll make the numbers change, but it will affect the what as far as the vector goes. Any ideas? The length, the magnitude. It'll just stretch it or shrink it, depending. So if I have an original vector here, and I say, okay, make k 2. Well, it's just going to double the length of it. What if I instead I made it negative 2? It's not going to shrink it.
Change the direction.
It's going to flip it. It's going to change the direction. Its slope is going to be the same, but instead of going up to the right, you'd be going down this way. Okay, but remember, the position I can change. I can put it up here instead. That's the same thing, these two. So if I have, doesn't matter what I'm multiplying by, I may change the direction it's pointed, but I'm not going to change its overall slope just by changing that k value. I'll change the length. I might change the direction if it's negative, but just stretching or shrinking the thing. Does that make sense? Okay. Now, as far as the addition goes, addition is a little bit of a slightly stranger concept. Because you're adding the components, graphically what's going on is you're taking a vector u and a vector v, and you're tacking one end, or the initial end of one, to the terminal end of the other. So if I have these two vectors u and v, and I want to add v to u, I'm literally going to move v up to here so that its initial point touches the terminal point, or shares the terminal point with u, and my combined u plus v is going to be from the initial point of the one to the terminal point of the other. Now u plus v, or v plus u, they're the same thing. So instead I could actually take u and move it to the end of v. It would give me that same vector direction and magnitude. Now arithmetically, that's very simple. All you're doing literally is adding the x's, adding the y's, if you put it to the origin first. If you put it in component form first, all I have to do is add the x values, add the y values, that's your new vector. That's why we use component form a lot, because then I don't have to worry about where things end up based on the, like, terminal is at 7, 8, initials at 4, 3. I can just move everything to the origin, and then just add the x's and y's. Scalar multiplier, just make sure you distribute the k to everything inside that vector. Okay? Negative addition works, or subtraction works a little bit strangely as far as the visual goes. Arithmetically, it's easy. You just subtract instead of add. But what's actually going on here? If I think of u minus v, well, that's the same thing as adding negative v to that u, right? So if I have the vector u here going from the origin out, I have the vector v going from the origin out. Well, if I want to add negative v, well, what's a negative v going to do to this? What's the negative out front going to do? Change, so it's going to flip it. So it's going to, instead of starting at the origin going out, it's going to start here and go in. So then I'm just going to take that, invert that negative v and move it up until its initial point is at the terminal of u, and then follow that to its end. So now I go from the initial of u to the terminal of v. So my vector ends up right here. That's the vector u plus negative v, or u minus v. So it's a little bit strange to visualize what's going on there, but it's basically turning this thing into, and they're going to be a bunch of parallelograms. If you're doing minus, they're giving you one of the diagonals. If you're doing plus, they're just giving you the outside edges of it. Okay? Now, drawing the visual, you're not going to have to worry about too much. It's good to practice it. It becomes necessary in some of the three-dimensional ones to be able to keep track of where everything is, because things start to move very weirdly when we get there. Okay. But if you're just looking at the vectors as numbers, it makes it much, much simpler. What would I get for u plus v given these two vectors u and v? What would the combined vector be?
4 and 3.
Yeah, 4, 3. 1 plus 3 is 4, 2 plus 1 is 3. What about if I had the vector u minus v? -2 and 1. Just take the vectors, the parts of u minus the parts of v. 2u minus 3v. Do that in 2 steps just to keep track of all the moving parts. What would you get for 2u? 2 and 4. You literally just double everything in u. What about for 3v? 9 and 3. Triple everything. Yep. Then subtract them. You get what? -7 and 1. So none of the math today is that bad. It's just keeping track of all how everything's interacting. Okay, vector operations. Now these are the properties of vectors. There's a lot here, but in reality, you know all these. U plus v is equal to v plus u. That's just the reflexive property. They're showing you the properties that apply: the reflexive, symmetric, commutative, associative. This is just those same properties. These work for addition as well as scalar multiplication. Now, just like with matrices, though, they don't work with matrix multiplication. They don't work with some of the vector multiplication we'll do later. Okay, not in this section, but all your basic addition properties apply, and all your scalar multipliers. Distributive property works if you have something out front, distribute to everything, that kind of stuff. So all those basic properties you already know work. Okay, so you don't have to worry about the manipulation too much. All your regular algebra rules work for the manipulation. Now, sometimes it is convenient, though, to be able to take the vector as it is and shrink it so it is exactly 1 unit long, so it becomes a unit vector. The way you do that is just to, well, if you have a coordinate, say 3, 4, then your magnitude would be 5, right? 3, 4, 5, triangle. So if I wanted to shrink it down to 1, instead of going over 3 up 4, I'm going to go over 3/5 and up 4/5. All you do is take it and divide by the magnitude. You just take your vector, all the parts of it, and divide each part by whatever that magnitude of the vector is. That's going to shrink it. It's going to maintain the direction it was going previously, but it's going to shrink it down to a unit vector that's in the direction of what v used to be. Does that make sense? Okay. Let's actually do that. So if I want to find a unit vector that's in the same direction as what 7, -3 is. Well, first off, I need to find what? Yeah, the current magnitude. So I need to find the magnitude of v. Well, that's going to be equal to the square root of what?
56. 7. 8.
Tip. You can do the squaring in your head. Don't try to do the squaring and the addition because you're likely to make a mistake. What 2 numbers am I adding together underneath the radical? 49 and 9. 49 plus 9 is 58.
I guess that.
Eventually. So you get the square root of 58. Now, if I want the unit vector then, I'm going to take that magnitude underneath the vector v. So what that means is I'm going to take the original 7, -3 and divide both components by the square root of 58. Now, honestly, the unit vector thing is usually used as a step to do something else later. So I'm not going to make you rationalize the denominator. You can just leave it this way. Okay? Because typically you're going to end up doing something else with it. Starting off, it'll be find the unit vector. Now, how do I actually verify this thing that it is a unit vector? Find the magnitude of it. So I want to find the magnitude of this new u vector that we just found. Well, for that I'm going to take the square root of what? Yeah, you take each component there and square it and add them up. Well, what's 7 over the square root of 58 squared? 49 over 58. Square the top, square the bottom. What's the other one squared? 9 over 58. 49 over 58 plus 9 over 58 gives me 58 over 58, which conveniently is your square root of 1, which is
1.
1.
Wow.
Okay, yeah.
So a unit vector, it doesn't have to be in standard position.
Technically not, but most of the time you're going to be working with it, because to do the unit vector, you're going to want to take that component form, which is in standard position, divided by the magnitude. So you're gonna get it in standard position every time,
Okay.
because to do it, you need to take this form, that component form, divided by the magnitude.
Okay.
So your resulting one will always be in standard position when you do that. Does that make sense?
Yeah.
Anything else so far? Okay. Now, these unit vectors are convenient for some other things we do with them later. So they actually define some standard unit vectors. Your standard unit vectors are the ones that go literally straight along the x-axis and straight up the y-axis. So it's just a unit vector I, and this is that bold letter. It's kind of hard to see, so I'm going to change it to an arrow. And j are just those vectors that represent the x-axis that's 1 unit long, the y-axis 1 unit long. Okay, so they'll use I and j, and then I'll use k when we get to the z-axis, when we do 3 dimensions. Now, they do use I, and it's annoying, but they were developed at 2 different times using the same set of letters. So don't mistake this I as an imaginary. This is the vector I, not the square root of -1i. Okay? Now, the reason we want to do that is because it allows us to write things another way. It's kind of like we have slope-intercept form and we have standard form for lines. Well, sometimes one's more convenient than the other. Well, they have component form for vectors. They also have what's called a linear combination form. Now, the concept here is if that I have, and I'm going to work this backwards. If I had a vector 1, the x component of a vector, okay, in other words, how far you're going over on the x, times the vector I, plus the y component times the vector j. Well, I and j are just 1, 0, and 0, 1. So if I take v1 times 1, 0, I'm going to get, and they're kind of skipping this step, I'm going to get v1, 0. I'm going to add to that 0, v2. Well, if I add those two vectors up, I get the component form. Okay? But really, you don't have to go through all the process of it. All you do is take the v1, slap an I after it, add together with v2 with a j. So if they want what's called a linear combination, they want just the horizontal part and the vertical part separated out. Okay? So it's a linear combination of vectors I and j. Does that make sense? So you need to be able to differentiate between those two, linear vectors and component form. Sorry, linear combinations and component form. So if I have the vector u as initial point -2, 6, terminal point -8, 3, I want to write u as a linear combination. Well, I'm going to turn it into component form first. What would component form of this vector u be? You subtract the terminal minus the initial.
Okay. 6. -3. -6, sorry.
-6, -3. So you literally just took -8 minus the -2 and 3 minus the 6. Terminal values minus the initial values. Now if I want this in linear combination form, well, it's still a vector, but now I'm going to take -6 times what? I.
Not the imaginary I.
Correct. Minus 3 times j. That is your linear combination of this.
That's really easy.
Yes, it is. It's just a matter of keeping the terminology straight.
So I is the x.
I is the horizontal movement, which is the x-coordinate. J is the vertical movement, which is the y-coordinate. Okay? Now, the nice thing about this form, especially, is that it allows you to think algebraically. You can treat I and j just as if they're variables. So if I have u is the vector I plus j, v is the vector 5i minus 3j. I can just literally take this and think of those as variables. I'm going to take 2 times I plus j minus 3 times 5I minus 3j. So that's going to give me what on the left? Yeah, 2I plus 2j. Distribute the negative 3. Negative 15I.
15J.
Plus 9j. Okay.
1 by 5.
Add them up. What do you get for the I? Negative 13I. Then? Plus 11j. So there's your component form of the combined. So it turns it into just a regular old algebra problem. Just happen to have these weird arrow things over your variables. And realizing what those variables represent. Okay. Now the other thing you can do with the I and j is actually use the fact that a horizontal movement, it's a lot in this section, the horizontal movement, if I actually define that to a unit vector, the horizontal movement is actually just something straight off the unit circle. Because the unit circle, any point on there, if you went from the origin out, is going to have a magnitude of what?
1.
1. So the idea is I can have a vector anywhere on that unit circle that's represented by cosine of theta, sine of theta.
Escape trig functions.
Still a trig chapter. So I can also represent that by taking whatever the cosine of theta is times I plus sine theta times j. The reason I want to do that theta is your direction angle. Rather than having the direction given as a slope, you can give the direction as an angle theta. This is the idea of the transfer between polar coordinates and rectangular coordinates. These direction angles, though, because of this, if I just have cosine theta and sine theta as a vector, then the magnitude of it is 1, right? So if I want a vector that's in any direction but longer, I can take whatever that theta value is and just multiply it times the magnitude. Or I can do it in component form too. Because all it's going to do is take that unit vector that's 1 unit long and stretch it by whatever that magnitude is. Okay? And I can also work this the other way as well. Now, this theta value, though, you always want to go from the x-axis up. You always want to think of your normal unit circle from the x-axis counterclockwise for theta. Okay? But I can also think of that backwards, too. Because tangent is equal to sine divided by cosine, right? And if I have magnitude times sine, magnitude times cosine, that's literally just the rise and the run. This is just slope. So you can transfer between theta and slope very, very easily just by dividing your y component by your x component. And then setting that equal to tangent theta. Good. B and A, they're giving that to you here. If vector v, that's v1 and v2. That's just literally the x component and the y component. So on a problem, what that's going to look like is if I want to figure out the direction angle, I want to figure out theta for this. Well, I have here essentially a rise and a run, right? The rise is what? The run?
Negative 6.
So if I put those over those, that's the slope, right?
Yeah.
That's going to be equal to tangent of theta. So what that allows me to do then is find theta. Because tangent of theta would be equal to negative 1. And think unit circle. When is tangent of theta negative 1? 3 pi over 4, or if I was doing degrees, it'd be 135 degrees. So if you do inverse tangent, the idea is you get 135 degrees. Now, for the other one here, you have tangent of theta is equal to what?
Negative 4 over negative 7.
Negative 4 over negative 7. Now that one's not a convenient one on the unit circle that I already know.
True.
So what would you need to do? Inverse tangent on your calculator. Go ahead and do that. Stick to degrees. What do you get for theta?
29.74.
Everybody get 29.7 degrees? Too bad it's wrong. Why is it wrong?
I don't know.
What? Yeah, remember, this is an x and a y, right? So up here it's not bad. Negative 6, or negative 6, 6 is just right here. Well, that's 135 degrees. Negative 7, negative 4 is in which quadrant?
Third.
Third quadrant. So 7 left, 4 down. So you're down here. 29.7 won't work.
Add 180 to that.
Add 180 to that.
Oh, man.
So you get 209.7 degrees. Does that make sense? Okay, next. We'll do one more example. I'll save the last 2 examples for tomorrow.
Oh, those are the word ones. Okay.
Yep.
The word ones too.
I want to find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle 45 degrees below the horizontal.
Thank you, Crash.
Now, if you're thinking about it in terms of a vector, the 45 degrees is the what?
Angle of descent. Is that right?
Yeah.
Oh, yes.
But as far as a vector goes, what do we call it?
Oh. Slope.
Slope or direction. It's not actually slope, but it's direction.
Direction.
The magnitude then is the 100 miles per hour. Okay? So what I want to think of is that's how long the line, the length of the line represents that 100 miles per hour. So I'm going to draw a line down from the horizontal at a 45 degree angle. That's 100 units long. Those units being miles per hour. Okay? So then I want to turn this into component form though. So I want to represent this as a coordinate. Okay? It's not going to crash. It's way up there. Anyway. What I'm going to do then is I'm going to take this and rearrange it so I have a unit vector instead. In other words, I'm going to take it times cosine of that theta value and sine of theta value, but I'm not going to do it as only 1 unit long. I'm going to do it as 100 units long. I have a vector here. Let's use v. So in this case, the magnitude of v is what? 100. Cosine of theta. Well, what's theta?
45.
Careful.
Oh, my goodness.
Yeah. Negative 45 you could do, or you could just do 360 minus 45, which is 315.
Yeah.
Either way, what's the cosine of 315 degrees?
Wait, square root of 2.
Square root 2 over 2. Sine?
Negative square root of 2.
So if I want component form of this vector, I'm going to then take the 100 and distribute it. What's 100 times square root of 2 over 2?
Yes.
50 root 2, yep. And then times negative will just be negative 50 root 2. So this is the component form of that vector. Questions on any of it? There's a fair amount. Was the math of it, the math manipulation you're doing, that bad?
I thought you were going to end about 50 times and you kept using new terms. And I was like, oh my god.
Okay, we will finish up the last of it.